Okay, the second talk, I want to cover these subjects. Here we got some math associated with the half-life calculations. When I go through that, just remember it's the same thing that we did in chapter 14. Okay, we'll see equations that are similar to what we saw there. This radioactive isotope is the only chemical or nuclear equation that we're going to worry about here. And then down here, this is mainly concepts in terms of the use and dangers of radiation, and throw some examples and units at you in terms of explaining some of these issues associated with radiation. This first reaction, synthesis of a radioisotope, some books use the term bombardment reaction when you're talking about the synthesis of a radioisotope. And what they're talking about here is bombardment. You're slamming things together, and we'll see it actually in the last presentation as well when we talk about nuclear fission, when we're breaking apart nuclei. For example, here, balanced nuclear equation for the formation of polonium-240 from polonium-239. And so this is one of the reactants. And then this is the product. And the question is, what do you slam into this thing to cause this particular transformation? And we're approaching it the same way in terms of like balancing these equations. We do it the same way as we saw in the first example. 94 plus 0 is going to equal 94, and then 1 plus 239 equals 240. And that is representative of a neutron. And so what's happening here is this polonium-239 is capturing a neutron and then converting over to polonium-240. That is a bombardment reaction. We'll see another one in the next lecture. I'm not going to do many problems with this because the balancing act is the same as what we saw in the first presentation. Really what I want to concentrate on in this presentation is this issue of the kinetic calculations associated with radioactive decay. Where to start here? I guess one thing to actually let's start with this graph down here. This is a decay graph for a particular it's a strontium-90 isotope. We're starting out with 10 grams at a 0 time, and then by the time we get to 100 years out into the future, 1 century later, we're left with about 1 gram of the substance or so. As it turns out, this is an exponential decay, and what it does is it follows a first order reaction. The conclusions from the first order reaction back in chapter 14 were these two equations up here. Now it's rearranged just a little bit, but this is the integrated rate law for a first order expression, and then this is the half-life formula for that particular expression. Notice, the rate of decay here is not a function of the concentration of the radioisotope, so it doesn't matter if we start with 10 grams or 100 grams. The rate of decay, the rate at which this thing drops off is independent of the concentration. So what it's showing is that the strontium-90 is just sort of it's falling apart by itself over time at a constant rate. And the next three problems illustrate how to use these particular equations. Now, back in chapter 14, back in chapter 14 it was actually A that was used as a label there, and I think they probably had brackets around A, talking about concentration of. It would have been in molarity. Well, that's not what we see for this particular chapter. Now, it can be amount, and we sort of see an example like that coming up, but most times what you see is a measure of activity for the radioactivity. So we're not measuring, I mean, we have grams here of the strontium-90, but if we want to measure, just how radioactive this thing is, and we would use a Geiger counter or some other measuring device to measure the activity, or how hot is the sample. And so that's really like when I used radionucleotides in grad school. We used the term hot whenever we were talking about a radioactive substance, and they would be the substances would be delivered with a certain label indicating the activity that you have in front of you, and usually it is millicurie, and I'll talk about these units here in a second. But essentially what you're saying about activity is disintegrations per second. If you have a really hot substance, a very radioactive substance, and it's falling apart and it's kicking off many alpha particles or beta particles in the process per second, and so you have a high activity. And we have units that describe the activity of a substance. Now, actually, in the problems that we use is actually disintegrations per second or disintegrations per minute are actually the units that you come across, but you could just as easily come across Becquerel or Curie or millicurie, and all it's describing is again the rate of disintegration. For a Becquerel, this is the SI unit for activity for radioisotopes, and it's literally the disintegrations per second. So when we look at these examples here, like 15.2 disintegrations per second, we could just as easily describe this carbon sample as 15.2 Becquerels instead of disintegrations per second. And so the Becquerel is actually a direct unit, showing you how literally how hot it is. The millicurie, there's some math you have to do to convert between the two. I'm not worried about that. Millicurie is an older unit. It's actually more common. I used radioactivity or radionucleotides for a little bit in grad school, and my memory is it always came in as millicurie amounts, and that represented pretty much the concentration of the sample that we had in front of us. And the Curie unit, well, it's named after Madame Curie from early 20th century work on radioactivity, but it represents it's actually defined as a decay rate for 1 gram of radium, which is represented by 3.7 times 10 to the 10 disintegrations per second. And so it's not a direct, one Curie is not equal to 1 Becquerel. So there's a little bit of conversion. I'm not worried about it here. All I want you to do is recognize, what are these units? What are they telling you? And again, it's the activity. How hot is your sample? And like I said, well, in the problems, we see Becquerels. We see disintegrations per second. And I think in the third problem, disintegrations per minute, possibly. But there's a few flavors, if you will, for types of half-life reactions that we need to worry about. Now, one simple one is actually diagrammed by this graph here. What is a half-life? A half-life tells you, I think I did this in the first presentation, the half-life for this thing looks to be about, I don't know, what is that, 27 years or so? Something like that. So after 27 years, the 10 gram sample goes to 5 grams, and so on and so on. So if I start out with 10 grams here, after 27 years, I'm going to be left with that much. After another 27 years, I'll be left with that much, and so on. And so you can, for each time period that represents a half-life, then you can drop the concentration in half as you go down the chart here. So that's one way to do half-life determination. That's how this one is set up. Actually, it's very wordy. There's a lot of information being thrown at you, but essentially you have this, a synthetic radioisotope, carbon-11. They give you the half-life of 20.4, but you really don't need that in the calculation. All it's saying is that it's this last part that's important. What percentage of the original carbon-11 remains after 5 half-lives? Well, really, there's the easiest way to do this particular problem, in my opinion, is just to say, well, at the beginning I have 100% in front of me. After 1 half-life, I go to 50%. After another half-life, I go to 25%. Do you see where I'm going with this? You just go through 5 different half-lives. Let me just give you all the numbers that are in front of me here. 12.5%. It goes then to 6.25%, and then finally to 3.125%. That's about as simple a half-life calculation as you can get. And what you see is you got 1, 2, 3, 4, 5 different half-lives. I'm left with 3.125% of the original sample remaining. Okay? And that's it, really. Now you could go in here. I guess another possible question associated with one of these is, how much time does it take to get to 3.125%? And what's 20.4 times 5 half-lives? That essentially it comes to 1 hour and 42 minutes. These these tracers that are used in medical imaging and other medical uses, a lot of them have a short half-life like this. So there's a finite time that they can actually be used after they're created. I'm not, my little disclaimer from last presentation was that I'm not a nuclear chemist, so I get away with some things here. I'm also not I'm not in the medical sciences either, and so the medical field. I know that some of the radioisotopes are synthesized in-house, but the nitty-gritty detail of how these things are created, I'm not terribly concerned with. Now, the fact that carbon-11 has a 20.4 minute half-life, suggests to me it can't be too old in terms of when it's created and when it's used. After if you have 1 gram of this stuff, after an hour and 42 minutes, 0.03 grams, something like that. So, it's got to be made pretty close by. But again, that is about a simple half-life determination that you can play with. Now, the other 2 problems I have here are actually going to be, we're actually going to use our equation here, and I'm not sure how much room I need for this one, so let me just squeeze it up here. Again, this is a first order integrated rate law that we saw back in chapter 14. If I'm not mistaken, it's section 14.3. If you want to take a look, 10th edition, Brown and LeMay. You don't need to go back there. I'm going to show you how we're going to use it. The T naught, the 0 here, sub-0. This is the initial activity. Like I said, it could be amount, but usually what I've seen is that you're given some kind of activity for the reaction, for the radioactive sample, and then because that's what it's measured in. Remember, like whenever we got the container containing the radionucleotide in grad school, from my memory, is always in millicuries. So it's not really given as a concentration. I guess there's some information about concentration there, but activity is typically what is referenced. N sub T is, well, like in the context of this problem, it's the 11.6 disintegrations per second. It is representing the activity of the actual sample that you're looking at, at some time t in the future. What's happening to this carbon-14 in the sample? Well, you start out initially when it's formed, and it's decaying somewhere along this pathway is what you're trying to figure out. The 15.2 is what you're beginning with, and then you're measuring an activity of 11.6, and you're trying to figure out what is that time, how old is this object. So this is carbon-14 dating, essentially, what you see here. Carbon-14 is formed as a trace amount on this planet. It's an interaction of ionizing radiation. I can't remember which isotope it is, but and then it's taken in the normal carbon cycle on the planet, and it's trapped in organic biological tissue. And so some some biological tissue that's, I can't remember the exact cutoff date, a few thousand years old, then you can use carbon-13 dating, very much how we're doing it here, to approximate the age of the object that you might find. But it does have to be a organic object, like a flint from a arrowhead. It's not organic. Some kind of a metal jug found, a metal pot found somewhere. As a coin, it wouldn't work. It doesn't have any carbon. It's got to be wooden. It's got to be tissue, plant material, something like that. That's involved in the carbon cycle on this planet. Anyway, the half-life is given to you. So that's T 1/2 is the 5715 years. So it's a pretty long half-life. And so when you do these calculations, it's really a combination of both of these equations. Like, very common technique is that you're going to use, like in the problem that we're looking at now, the T 1/2 is given, the K is not. So we can easily calculate the rate constant for this particular isotope using the half-life that is given in the problem. And so to do that, if we calculate K here, what it does is it sets us up to where we can plug K into our expression here and then solve for the T, because we're wondering what is the age of that archaeological sample. So that's a very common layout for these types of problems. If I rearrange the expression, it's simply 0.693 divided by the T 1/2. One thing you really need to watch out for is the units of time on this. Now, in this particular example, they're talking about years in the context of the half-life. They're talking about disintegrations per second in the context of the activity. You got to change the units so they agree. Now, what I chose to do is to change years to seconds, and that gives me a value of there it is, 1.802 times 10 to the 11 seconds. Actually, maybe I should just go ahead and do that. It's sort of a long-winded dimensional analysis problem. I'm hoping that you sort of see where I'm going to go with this. I'm not going to talk much about it. In 1 year we have 365 days, right? You should know that. And then in 1 day we have 24 hours. You should know that. 1 hour we have 60 minutes, and then in 1 minute we have 60 seconds. So it's just a big dimensional analysis game. Years cancel out, days cancel out, hours cancel out, minutes cancel out. We're left with seconds. Okay, that's the setup that you got to do for this. And then in the second part, I think I backtrack. I have to go. Yeah, I do. I go from seconds to hours. So I use the same conversion factors. Just I invert them along the way for the calculation. I'm not going to show that one. So this is something that should look familiar to you. If you want me to, I can talk about it in class, or come see me in my office. Okay, so now we have the half-life in terms of seconds. If I plug it into this expression, I'm going to get a K value of 3.846 times 10 to the minus 12 inverse seconds, which you may have forgotten, but that is the unit for first order rate constant. So we're good there. And now what we can do is we can just plug all these values in. And I'm going to drop the units, disintegrations per second on both of these units, so they're going to fall away as I do this calculation. So I'm not going to bother carrying them through. And point 2, the K, don't forget the negative sign. And remember, I mean, for the test, I'm going to give you this equation anyway. You just need to be able to use the thing. 846 times 10 to the minus 12 inverse seconds. And then T is the unknown. So we solve for T, and what we come up with is, well, the first number you'll come up with is plus 10 seconds. What, 70 billion seconds, I think, is how to, yeah. Well, we don't want that. We want years. 2229 years is what I calculated. The book is 2,230 years, so we're good. This is correct. That's the basic layout. You use the half-life to determine the rate constant, and then in this expression, something will be missing. Two of the three other things will be given. Like in the next example that we look at, notice that so the half-life is given as 110 minutes. What percentage of the original activity remains after 300 seconds? So actually, or 300 minutes. And so the t is given in this one. T1/2 is given at 110 minutes, and that's it actually. Right? Well, what else are we looking for? Let's see. Let's get this up here so we can see what we have, see what we need, see where we're going. The t is given, that's the 300 minutes. K can be calculated from this guy, and actually I'm just going to give that to you. I used the same method as I used on that last one. And this one I don't need to switch to seconds because of the units agreeing here. So I'm just going to leave it as inverse minutes. So I have that one, and then I'm wanting to know how much of the sample is left after 300 minutes. So it's actually the n sub t that I'm curious about. What do I do with the original sample? Well, I mean, it's asking for a percentage, so I'm just going to say, what do I start off with initially? I start with 100%, and then as it goes through, let's go back to that graph. If I start with 100%, then as it starts decaying, then there's going to be a certain percentage left over at 300 minutes in this particular problem. I guess what I could have also given the value of 100 grams or 1 gram, and then find the percentage at the end. I could do it that way as well, but I just chose to just use 100% for my initial activity for this example. And if I plug all of these values in, negative 6.3 times 10 to the minus 3 minutes, notice that it's actually at this first step where the minutes cancel away. So that's why I didn't bother converting this to seconds, because I don't need to. The reason why I did it here is because the disintegrations per second and then the half-life were given in two different units, so I had to bring those two together in the same unit for agreement. Here I don't really care. I guess that, well, the half-life and then the t were already given in the same unit, so I don't have to worry about it, and they cancel out in this first part of the calculation anyway. Just a reminder how to handle the natural log here, and there's a couple of approaches that you could use. This is how I did it. This value is actually negative 1.89 when if I calculated these two. So if you have a division problem within a natural log, you break it apart, and it's a subtraction process for the two. So to solve for this, let's see, natural log of nt. Once I take the natural log of 100 and then add that to both sides, I'll get 2.72. And then remember, to get rid of the natural log, you take the exponential of both sides. And so the exponential is taken on that side as well. And then what that does is it tells us we have 15.1% of the original sample left over. This is not something you have to use this formula sometimes when you're doing a half-life calculation. In some ways, this particular approach looks very similar to this kind of calculation that we did before. We have a half-life. We started out with 100% here, and then in this case, we went through 5 half-lives to get to the percent. Well, we have a certain percentage left over after a certain period of time. This isn't so clean cut. It's not as simple. You have to use these equations to figure out what that percentage at the end is going to be. Okay, so those three examples pretty much cover what you got to worry about for the half-life calculation. So keep these close at hand when you're working on the quiz and studying for the test. The rest of this presentation is all conceptual. There's no real calculations going to show up in the next few slides. So there is a part of the chapter called Chemistry and Life. It's a separate box that is inserted into the chapter of, I can't remember which section it's in, but it talks about the use of radioisotopes in the medical industry, in the medical field. And I just want to sort of expose you to a little bit of conceptual things about radionuclides and radiation. You know, not all radioactive substances are dangerous. I mean, I guess they're all dangerous in the sense they cause damage to the body, and we'll talk about that here in a few minutes. But, you know, they do special things, and we have, or scientists have developed methods to take advantage of their radioactivity to monitor and follow certain processes inside the body. And there's a few examples here. I'm not going to ask you, specific questions about what does this nucleotide do in terms of study of the body. I won't ask that. I'm asking mainly, what's the basic layout of one of these things? How does it work? For example, you're going to actually incorporate the radio. It's not that you take some kind of metal tablet and you ingest it. What happens is that these different radioisotopes, such as especially like something like carbon 11, it can be incorporated into glucose, some kind of there's organic compounds all over the place, and so you can incorporate these radio tags, these radio tracers, into an organic substance, a food source, and then ingest it. And then what happens is that system, that compound, it carries through the body, and then the radioactive, the radioisotope leaves a trace of its, or not a trace of itself, but it sends a signal out within the body, and then there's methods used to detect the signals that are coming out. And so what happens is that now the radioisotope, depending on how it's packaged for ingestion or administered intravenously, it's going to concentrate in a particular region of the brain or a particular organ of the body, and then there are these methods that are used to determine where that has accumulated. For example, the testing of there it is, right there. The testing of a thyroid condition. If I'm not mistaken, it's a solution of sodium iodide, where this iodide, there's a certain concentration of iodide that's 131, and what happens is it concentrates in the throat, in the thyroid gland, and then a Geiger counter would be placed up to the thyroid to detect the radiation that's being kicked off of it. That's a fairly has a fairly low level of sophistication in terms of identifying where that iodine is concentrated. An overactive thyroid would show that kind of signal. And I guess a normally active thyroid has a level somewhere in the middle between like hyperthyroid and hypothyroid conditions. If someone's been exposed, there's iodine 131 is used in biological research, and if someone, iodine is pretty good at subliming, and so when you open up one of those that sample of that's radioactive, there's a little bit of gas right there, and if you inhale too much of it, it'll actually collect in the thyroid, and the radiation safety workers can check whether you're exposed to the iodine by placing a Geiger counter up to your thyroid and see if you have a high signal or not. Now, a more sophisticated method that can be used is positron emission tomography, PET, And I do have a little picture. I pulled the pictures from the textbook. I didn't get any real fancy here or anything. And what's happening is, I don't think the textbook does a great job at this, but what happens, the positron emission, so we have I can't remember an exact one that was undergoing positron emission. Let's see, the magnesium 22? Yeah. I don't think it's used in a PET scan, but that was an example from the first lecture that would undergo positron emission. But what happens here is that when that positron is kicked off, oops, the wrong way. That's the symbol for the positron. When that thing's kicked off in the body, it's actually not the positron that's detected. What happens is that there's a collision with another substance. I can't remember, but it actually gives off a gamma ray. Gamma rays are very good at penetrating tissue. They're very good at penetrating solid objects. You know, it takes 6 to 12 inches of concrete to stop a gamma ray. It doesn't take that to stop any of the other types of radiation that we've talked about here, because they're much larger than the gamma ray. And so what happens is that when you look at, you know, so the chemical concentrates in different portions of the brain. This is for obsessive compulsive behavior. And they're doing a PET scan of different slices of the brain. You can see that there's different regions of the brain that are more active with that particular disorder. And so they can localize, you know, where does that occur? I'm going to think of this as some kind of just research at a university, just trying to understand the psychological, the physiological causes for that psychological behavior. But it's not the positrons that are being emitted or detected here. This large, strange-looking device is picking up the gamma rays that are coming out of the brain. And it can the computer system can then sketch these three-dimensional structures for the organ that's under investigation there. And the book, I don't think the book talks much about, you know, exactly what's being detected there. Okay, another concept that we want to talk about. You know, yeah, it's emitting from the brain. There's, as long as it's a low dose, I don't know, radiation, it's not life-threatening. I'll put it that way. You know, I get one set of dental x-rays per year, and I don't freak out about it. I'm okay. Now, the technician that is probably doing that a few dozen times a day, notice that he or she steps behind the door, or they put on a lead apron. If they're exposed repeatedly to radioactivity, then it's an issue. And then you get into things like this, these units that are talked about for the sources of radiation, and then ultimately the absorption, and then the effects of the radiation. So the first thing I want you to appreciate that, you know, not everything that's natural is good for you. There are plenty of natural sources of radiation. When the radiation workers came into the lab at Chapel Hill, when I was a grad student there, you know, they would take a background test for the radiation. They would hold their Geiger counter out and find out what is the level of the radioactivity just normally in the lab. And so then they would compare that to, you know, how much radioactivity is showing up from a contaminated part of the workbench, something like that. And you'll see in the lab that you do for this, there's an issue with the background radiation as well. But there's all kinds of sources of radiation on this planet. There's cosmic rays, which actually the cosmic rays, I can't remember the exact mechanism for this, but cosmic rays is what generates the trace amount of carbon-14 that's used for the carbon-14 dating. Rocks and soils, you know, there's plenty of just naturally occurring radioisotopes that are found in rock formations. And then one of the big dangers, especially in this area, is radon gas. This is a colorless, odorless, radioactive gas that can leak into your house from underground, and it can if your house is a fairly modern house and nice and tight, and it doesn't it's not very drafty, then the buildup of radon can be pretty dangerous. And just FYI, I think Department of Agriculture in North Carolina will provide a free test kit so that you can test the level of radon in your house. I would advise doing that, because this particular area of the country is prone for a large amount of radon coming out of the ground. But just be aware that there's certain sources that are naturally occurring, and then we see some X-rays, nuclear medicine, consumer products. I'm thinking of a fire alarm that has a little bit of americonium, I believe, and I guess there's a radioactive source in a detector detecting that radioactivity, and then when particulate matter gets in the way, then that signal changes, and so then it sends off the alarm saying, oh, there's smoke in the air. And so that's probably what they're talking, one of the what would be under the category of consumer products. Notice that the unit that's associated with the this table here is millirem, and rem is coming from this equation here, number of rems, and it's essentially, think about the rems as the amount of damage that's actually occurred to your body, kind of thing. It's not the amount of radiation that's absorbed. That's a different thing. Notice that the amount of radiation that's absorbed is referred to as a rad, and that is embedded within this formula for the number of rems. So these are some of the units and concepts that I want you to be familiar with for this course. And this RBE, relative biological effectiveness, well, this depends on the type of radiation that you're actually absorbing. So even though, I talk about gamma radiation being very good at penetrating flesh, remember it takes, 6 to 12 inches of concrete to stop gamma rays, but notice that the alpha particle, that big, fat, slow particle that we looked at in the very first presentation, actually has a larger relative biological effectiveness. This means that it's more damaging than gamma rays. And I'll explain what I mean by that here in a minute. But the RBE is essentially, think of this as like biological damage that a particular type of radiation can do to the body. The reason why the alpha particle is so dangerous because it actually doesn't penetrate very well. For example, if we look at the next slide, it sort of helps explain. This is our alpha particle. Remember, it has that RBE of 10, and then these two have an RBE of 1. Now, don't get me wrong. I don't want to stand in front of some radioactive source kicking off a bunch of gamma rays. That's not fun. But when the gamma ray strikes your body, it passes through all the way, whereas an alpha particle, actually, if it's on the outside of your body, it's not a big deal because the first layer of skin can actually take that damage without really any big issue. What the problem with that high RBE for an alpha particle is that if you ingest the alpha particle, so if you've ingested some kind of a radioactive contaminant that is an alpha particle, what happens is that now the radioactive substance is inside your lung tissue. An alpha particle is emitted, and in a very short distance it collides with a cell. It collides with your DNA. It collides with a protein. And what happens is it starts doing a high level of damage locally where that radioactive source is in your lungs or wherever you've ingested it. Whereas a result, a gamma ray, if this substance is kicking off a gamma ray, then it has a chance of making it outside the body because it's so good at penetrating through tissue. That's why these substances here that are kicking off the gamma ray passes through pretty well, and this is a low dose anyway. You do one in your lifetime, and the benefits that you gain from the medical diagnosis is much greater than the harm that you get from the radiation, at least in my humble opinion anyway. I wouldn't want to get 2 PET scans a week or anything like that, but one to diagnose cancer, bring it on. That's great. Okay, last thing, we have the unit of rem showing up again. Please note, this rem, REM, it's the same measure, but it's on a different scale. This is millirem. So even radon, which is, I forget my stat exactly, but it's up there in terms of substances on this planet, either man-made or naturally occurring, that is dangerous to you. I mean, a bullet is more dangerous, of course, but radon is up there. Cigarette smoking is more dangerous. Alcoholism is more dangerous. Possibly a big juicy steak every night is maybe more dangerous. But radon is up there, but it's still at a millirem level. So it's 1/1000th of a rem. The reason why I point that out is because to put it in perspective is what I'm trying to do. So 200 millirem is radon, and that's pretty bad as those things go. And then actually let's bring in a medical X-ray. There's a good one. 39 millirem? Let's keep that in mind as well. 39 millirem for an X-ray. That's my dental X-ray that I'm getting once a year. No problem. It doesn't worry me. 0 to 25 rem, so 0 to 25,000 millirem, no detectable clinical effects. That's great. That's why I'm not so worried about that one medical X-ray that I have per year. Or if I have to have that, I've never had a PET scan before, but if I have to have one, I'm not going to freak out about it. I'm going to freak out if, a Hiroshima-type bomb is dropped in the middle of Asheville and I'm sitting in my office. Pretty much, if that did happen, for a Hiroshima-type bomb, which is, as atomic bombs go, fairly wimpy nowadays, and low sophistication, it's going to pretty much level, obliterate the first a diameter of a few miles around the explosion, where the initial explosion occurs. So I would essentially be leveled pretty much. I would disappear practically. That's a problem. The long-term effects of survivors of the Hiroshima and Nagasaki bombs dropped in 1945 to end World War II. That's a problem. You have lingering radioactivity in the environment, and the humans have to live around that. That's when you start getting these higher levels of exposure to the radiation, and that's where you get not just nausea. I can deal with nausea. It's this horrible stat here. Death to half exposed after 30 days of exposure to the radiation. This is a level where it's actually probably Nagasaki, Hiroshima, and then maybe Chernobyl in that localized area. You could probably argue had that kind of exposure level. And I'm just sort of taking an educated guess at that more than anything else. I think I'm pretty safe in the Hiroshima and Nagasaki comment. They're still dealing with a higher incidence of cancer in the population than outside those two regions. So, radioactivity, it can do good things, but as we're well aware, it can do bad things too. And that's what we get to talk about in the third and final lecture for this chapter. Okay, so thanks.